Hi everyone, this is your math guru. In this video, I'm going to solve the following circle geometry examples by applying the appropriate circle theorem. Please don't forget to click on the like and subscribe button below for more easy to understand math concepts. In the first example, we have in the figure below, the line AB and CD are chords of the circle with center O. OE is perpendicular to the line AB. CF is equal to FD. If OE is 4 centimeters, OF 3 centimeters, and CD equals 8 centimeters, 1. Calculate the length of OD, and 2. Hence, calculate the length of AB. Inserting all the parameters given in the diagram, we've been told that the line OE equals 4 centimeters. I have that as 4 centimeters. The line OF, 3 centimeters. I have that as 3 centimeters. And CD equals 8 centimeters. The total distance CD has been given as 8 centimeters. However, CD is equal to CF plus FD. And because we've been told that CF is equal to FD, then it's divided by 2. CF will be 4 centimeters and FD will be 4 centimeters. 4 centimeters for 4 centimeters will give us the total distance CD. Solving the first part of the question, we have to calculate the length of OD. However, applying the circle theorem that states that the line drawn from the center of a circle is perpendicular to the chord and it also bisects the chord. CF is equal to FD, that's equal. Therefore, the line OF is perpendicular to the line CD. So that's a right angle. Drawing out the triangle, we have, going to draw a rough sketch here. I have the right angle, I have center O, I have D, and I have point F. FD has been given us 4 centimeters. We have OF to be 3 centimeters. We have to solve for OD. Using the Pythagoras theorem, the longest side, OD squared, is equal to the square of the sum of the square of the other two sides. So that's OF squared plus FD squared. The reason is Pythagoras theorem. Inserting the parameters, we have OD squared, which is the unknown, equals OF squared, that's 3 squared, plus FD squared, 4 squared. OD squared equals 3 squared, 3 times 3, that's 9, plus 4 squared, that's 4 times 4, 16. OD squared equals 9 plus 16, 25. Therefore, to find OD, we need to find the square root of both sides using the balance method. Therefore, the length OD equals square root of 25, 5 centimeters. So OD is 5 centimeters, which is 5. Note that OD is the same length as OB. That is, OD is equal to OB. That's the radii. That's equal to 5 centimeters. So therefore, OB here is 5 centimeters. Note that applying the same circle theorem that states that the line drawn from the center of a circle, if it's perpendicular to the chord, bisects the chord. And you can see the line is perpendicular, the OE is perpendicular to AB as shown. Therefore, BE is equal to EA. So therefore, to calculate the length of AB, AB as shown is equal to BE plus EA. To find BE, I'm going to draw that triangle. I have a right angle triangle as shown, such that if I have my right angle here, this is my B, this is the point E, and this is my O. I've been given OB, that's the hypotenuse, to be 5 centimeters. OE, 4 centimeters. I'm looking for my BE. So using the Pythagoras theorem, the longer side, your hypotenuse, OB squared equals OE squared plus BE squared. And the reason is Pythagoras theorem. Therefore, slotting in the parameters, I have 5 squared equals OE squared, that's 4 squared, plus BE squared. Making BE the subject of formula, I have BE squared equals to 5 squared minus 4 squared. BE squared equals 5 squared, 25, minus 4 squared, 16. BE squared, 25 minus 16, that's 9. Therefore, to find BE, I'm going to find the square root of both sides. Therefore, my BE equals square root of 9, which is 3 centimeters. So using the statement, the total length, AB, equals to BE plus EA, I calculated BE to be 3 centimeters, and it's also equal to EA, 3 centimeters. Therefore, the total length, AB, equals 3 centimeters plus 3 centimeters. Therefore, my AB equals to 6 centimeters. In the second example, I have in the figure below, angle DCO equals 25 degrees, and O is the center of the circle. A, B, E, C, and D are points on the circumference of the circle. Calculate, given reasons, the size of angles D1, A1, O1, and E. O is the center of the circle as shown, and we know that the distance from the center of the circle to any part of the circle is a radius. And because that's equal, I know that OD is equal to OC. I'm going to state that here. OD, the distance OD, equals to the line OC. The reason is radii. Therefore, triangle DOC is an isosceles triangle. And the property of an isosceles triangle states that the base angle of an isosceles triangle are equal. Therefore, D1 is equal to C, which is 25 degrees. To calculate A1, I'm going to take out the lines drawn. AB, D, and C are points on the circumference of the circle, and we know that angles in the same segment of a circle are equal. You can see the bow tie. I'm going to highlight that. I have AB, AC, DC, and line DB. Angles in the same segments are equal, and that means A1 is equal to D1. Likewise, my angle at B here is equal to my total angle at C here. Therefore, angle A1 is equal to angle D1, which is equal to 25 degrees. The reason being angle in the same segment. To calculate my O1, which is the next angle, I'm taking out the lines. You will observe that I have OD, which is part of the triangle DOC, extended to B. I have DC, that's part of the triangle, and I have OC. The external angle of a triangle is equal to the sum of the two opposite interior angles. I'm going to sketch that quickly. If I have a triangle and any of the side is being extended, the angle outside here, if I call this X, is equal to the sum of the two interior angle A and B. So therefore, X equals to A plus B. In this case, my O1, as shown, is my external angle, and therefore is equal to the sum of the two interior angles, D1 and C, which is 25. Therefore, my O1 equals D1 plus, I'm going to tag my C, this is C1, this is C2, C1. The reason being external angle of a triangle. Therefore, my angle O1 equals to D1, which is 25 degrees, plus C1, which is also 25 degrees. Therefore, angle O1 equals 25 plus 25, that's 50 degrees. To calculate my last angle, I'm going to take out the lines. You observe that I have a cyclic quad, that's AB, BE. Note that all the corners of my cyclic quad are touching the circumference of the circle. And the circle theorem states that the opposite sides or the opposite angles of a cyclic quad are supplementary or they add up to 180 degrees. We've been able to show that the angle at A1 is equal to 25 degrees. The opposite angle here is my E. So therefore, using the circle theorem that states that the opposite angles of a cyclic quad are supplementary, I have angle A1 plus angle E equals to 180 degrees. The reason being opposite angle of a cyclic quad. My A1 is 25 plus my E, which is the unknown, equals to 180 degrees. Therefore, my E equals, using the balance method, I'm going to subtract 25 degrees from both sides, which will give us 155 degrees. Therefore, my angle E is 155 degrees. In my last example, I have ABCD are points on the circumference of the circle in the diagram below. ECF is a tangent at C. B1 is equal to B2. I'm going to tag that quickly. Angle B1 is equal to angle B2. If B1 is equal to X, so I can replace that with X. As stated, B1 is X. Therefore, because it's equal to B2 as given, this is also X. Find with reasons two other angles equals to X. I can see my bow tie, that's line AB. I'm just highlighting the lines as shown. So therefore, using the circle theorem that states that angles in the same segment are equal, the angle at A is equal to the angle at D. Also, the angle at B1 is equal to the angle at C2. Therefore, I'm going to state that angle C2 is equal to angle B1, and we've been told that angle B1 is equal to x. So that is also equal to x. The reason being angle in the same segment. Putting that back into the equation, I have C2 equals to x. I need to find another angle equal to x. Taking out my lines again. Highlighting my triangle BDC. Remember, we've been told that the line ECF is a tangent to that triangle, and the circle theorem that states that the angle between a tangent to a circle and a chord drawn from the point of contact is equal to an angle in the alternate segment. That means that the angle C1, or this angle here, is equal to this angle. That is the tan chord theorem. So therefore, my angle B2 is the same as my angle C1, which is equal to x. I'm going to put that in the diagram. This is also equal to x. And the reason being, that's the tan chord theorem. Thanks for watching. Bye.